So here's where we left off on Thursday. We looked at the electron arrangements for the first 20 elements. That's as far as we're going to go in the periodic table. So what we see is we continue to add electrons in as we go up element by element. We increase the number of protons, we increase the number of electrons, and so we add electrons in until that level is full, and then we go on to the next energy level. For your purposes, all we're worried about is that n equals 1 has a limit of 2 electrons, n equals 2 and 3 have a limit of 8, and for n equals 4 we will only be adding in 2 electrons because we're stopping at calcium. We're not going to get into the details beyond that. So one thing we have to worry about in elements is not necessarily how many electrons they have in total, but how many valence electrons they have, because these are the electrons that are going to be involved in the bonding, whether we're forming ionic or covalent bonds, so electrons being shared or given or transferred, it doesn't matter, and we'll talk about what those words mean here. But what we're really worried about is how many are there. So when I look at fluorine, for example, I see that it had 2 electrons in the n equals 1 level, and so it has 2 electrons in n equals 1, and 7 in the n equals 2, and then going up to the n equals 3. So for fluorine, its valence are those 7 electrons. For neon, has 8 valence electrons. When I go on up to sodium, now I've got electrons in the n equals 3 level, and so those are my valence electrons. And what I see is that the electrons in the highest n value are those valence electrons, and those are the ones that are going to be involved in bonding. And you'll notice the same pattern as we go across. We go from fluorine, we have 7, neon has 8, sodium 1, magnesium 2, aluminum 3. We're basically working our way across the periodic table. And note that we've already seen this 8 before when we looked at these shells. We said, well, n equals 2 and 3, we're only going to fill up to 8 electrons. And what we notice is that if I look at my noble gases, so things in the group 8A, okay, looking for that group, I see neon has 8 valence electrons, and I see argon has 8 valence electrons. And if I continued on, what I'd find is that all of those elements in column 8A have 8 valence electrons. Those are noble gases, and that's where they're the most stable, is with those 8 electrons. So now we want to worry about, well, what do we mean, how do we know it's 8? Why do we worry about that number 8? Well, it turns out that's kind of a magic number. This 8, this octet, is that this is what noble gases look like. We know that noble gases are very unreactive. They're very happy the way they are. They don't want to gain or lose electrons. They don't want to do anything. They don't form bonds. They don't form compounds. They're just there all by themselves. So what we look at with other elements forming compounds is they want to look like the noble gases. They want to have that octet of electrons. There's a certain stability that comes with having that 8 electrons. And so what happens is atoms will either transfer or share electrons, giving up or taking, one way or another, to actually get to that octet so that they have 8 electrons around them. The two exceptions are, or the exception is for hydrogen, because it's trying to get 2 electrons because helium only has 2. Again, hydrogens are oddball out. It's not behaving like everything else. But for the rest of the elements on the periodic table, to have that 8 electrons in the valence gives it a certain level of stability. And so it wants to be like the noble gases. These are the atoms that everybody's looking up to. They've got a great electron configuration, a great electron arrangement, very stable, and as a result, all the atoms want to look like that. So how do we get to that? How do we form that octet? Well, there's 2 different ways we can do this. We can look at formation of cations or anions. So these are charged species that have lost or gained electrons. And what happens is these will form compounds. And there's actually a couple of videos online about ionic compound, figuring out what the formula is and the nomenclature. Here we're just going to talk about the fact that these ions form. And so if I look at sodium, when I look at the sodium at the nucleus, or at the atom rather, I have 11 protons. That means I also have 11 electrons because I have a neutral atom. Then I lose an electron, so one of my electrons is lost, and we'll talk a little bit more about where it's going in just a minute, but we lose an electron from the sodium, and then we have 11 protons and 10 electrons. Remember, I can't see a change in the number of protons because that's the one that determines the identity of the element, so the protons has to remain the same, but now that I have 10 electrons, I have more positive charge than I have negative charge, and as a result, I have a +1 charge on my sodium ion. Now, I typically don't write the 1 1 in there because if it's just 1, we can just put the plus or minus sign. We will see on other ions like magnesium forms a 2 plus that we're going to have write it as 2 plus and not just the plus sign. So when we look at our electron arrangement, going back to what we had talked about on the earlier slides here, we saw that we have 2, 8, 1 as my electron arrangement for the neutral atom. If I can lose that 1 electron, or if sodium can lose that 1 electron, then it has 8 valence electrons, 8 electrons in that outer shell, and it has the electron configuration that looks like a noble gas. When I look at the periodic table, I look right before sodium, and I see the element neon, and it has the electron arrangement of 2, 8. 2 electrons in the n equals 1 level, 8 electrons in the n equals 2 level. So sodium is just trying to look like neon. Well, what happens on the flip side of that? We said, well, sodium's giving up an electron. Somebody's got to take it. We can't just drop electrons off or pick them up randomly from space. They have to come from somewhere and they have to go to somewhere. Well, when I look at something like chlorine, I see that it has 17 protons and 17 electrons in the neutral atom. And so it's got 7 valence electrons because when I look at the electron arrangement down here at the bottom, it has 2, 8, 7. And so what I'm looking at is that it has 7 electrons. It has 2 choices. It can lose 7 or it can gain 1 because, again, it wants to look like a noble gas. And, in fact, it wants to look like argon, which has the arrangement of 2, 8, 8. That's the electron arrangement for argon. So when I look at chlorine, it says, wait a minute, if I can gain an electron, yes, that means I'll have a charge, but it also means I'll have my 8 electrons in that outer shell, and that's going to be a much more stable orientation for me. And so when I look now at the chloride ion, notice the ending changes from chlorine to chloride as it becomes an anion. We didn't see that in cations, but we do in anions. And now what I see is that I've got my chloride ion. I've got 17 protons and 18 electrons. I have gained an electron. I have 1 more electron than I had originally. I have 1 more electron than I have protons. So as a result, I have a -1 charge. Just like with the cation, I don't put the 1 in there because I have the minus sign and it's only a 1. If I looked at something that had a 2- charge, I would need to show that as, 2-. I can't just put a minus for that. But now when I look at the electron arrangement of my chloride ion, it's exactly the same as the electron arrangement for argon. So we see that atoms are going to do what they need to do in order to get to that octet. They want that and they're happy with the octet. So how do we find these charges? Oh, things got a little mixed up here when I switched over to the iPad to record this. So what we have here is, let me rewrite these in here a little bit better. We have 1 plus, 2 plus, 3 plus, 3 minus, so we can show that as 2 minus, and 1 minus. So sorry about the layout on that. What I'm looking at here, if I look at my first column of elements, I notice that these are all going to take a +1 charge. If I go back to my table of my electron arrangements, I'm going to see that they all have 1 electron in the highest n value. So hydrogen just has the 1 electron. Lithium has the arrangement of 2, 1. Sodium was 2, 8, 1. Potassium is 2, 8, 8, 1. So they're always going to lose that 1 electron so that they can look like the most recent noble gas, the nearest noble gas, which is below them in electron counts. When I look at something like magnesium, if I look at the electron arrangement of magnesium, so we have magnesium, we have 2, 8, and 2. So magnesium, in order to have 8, is either got to gain 6 or lose 2. Well, losing 2 sounds a lot easier than gaining 6. And so we're going to lose 2 electrons, and when it does, it will have the electron arrangement. So the magnesium 2 plus will have the electron arrangement of 2, 8. Again, it gets to an octet, but in order to do that, it had to lose 2 electrons. Therefore, it takes on a 2 plus charge because now it has 12 protons and 10 electrons, so a difference of 2. We're going to skip over the transition metals. We're not going to worry about the charges on them. They don't behave quite the same way because the electron configurations are getting a little bit little more complicated within the transition metals. When I get over to boron, aluminum, and gallium, I see a 3+ charge. I don't really worry about carbon, silicon, germanium. These technically could form a +4 or a -4, but the reality is that they tend to not form ionic compounds, and as a result, we tend not to talk about their charges, so because they just don't do it. So I get to nitrogen, or let me backtrack here. Let me go over to chlorine. So this halogens we talked about before. We said, well, chlorine needs to gain 1 electron to look like argon. Fluorine needs to gain 1 electron to look like neon. Bromine needs to gain 1 to look like krypton. And so we see all of these will take on the 1- charge because they're all going to gain that 1 electron. Oxygen has the electron arrangement of 2, 6, 2, 6, so it needs to gain 2 electrons. And so when it gains 2 electrons, it'll have 8 protons and 10 electrons, so it'll have a 2- charge. And the way we can show the oxygen or any of our anions is similar to what we did for the cations. We have our symbol, and we show the charge here of 2-. Going over to nitrogen's column, those will take on a 3- charge because they need to gain 3 electrons to look like the noble gas. Now let's look at some examples here. We lost a little bit of formatting when I converted over to the iPad, but which ion will have 20 electrons? And so what I can look at is if I have potassium, for example, I can look at the periodic table and I see that potassium is going to have 19 electrons because it has 19 protons, and neutral potassium will have 19 electrons. In order for it to become K+, that means it's losing electrons because I'm going to have 1 more proton than I have electrons. So K+ has lost an electron and therefore will only have 18 electrons because it will still have 19 protons in both the neutral atom and the ion. So in order to have a +1 charge, I have to have 1 more proton than I have electrons. For calcium, I can say, well, calcium has 20 protons, okay, and neutral calcium has 20 electrons as well. But if I go to calcium 2+, the 2 tells me I've had a change of 2 electrons, the plus tells me I've lost 2 electrons, because I'm still going to have 20 protons because that determines the identity of the element. But now I'm only going to have 18 electrons because I have to have more protons than electrons, and I have to have 2 more, so I end up with a 2+ charge. Last, I go to my titanium, and if I look at neutral titanium, I see that I have 22 protons and 22 electrons. And when I go to titanium 2+, I see that I'm going to lose 2 electrons. Again, the plus sign tells me I'm losing electrons because I want to end up with more positive charges than I have negative charges. It's kind of like your checking account. You want to have more deposits than withdrawals. And so here I have still 22 protons because that determines the identity. That does not change in a chemical process. But now I have 20 electrons. So titanium 2+ will have 20 electrons because it's lost 2. And I have 22 protons, 20 electrons. So plus 22 minus 20 gives me a +2 charge. So now what we're going to get into is ionic versus covalent. Again, there's a couple of videos already on Blackboard about the ionic compounds. The covalent bonds will be coming soon. Hopefully I'll have those up by Tuesday evening for you to watch so you can look at them. The key difference that we have to worry about is what's going on with the electrons. Remember, we're looking at chemical reactions, so we know that's where the change is happening. Therefore, what we have to worry about is what change is happening in an ionic bond versus the change that's happening in a covalent bond. So what we're looking at when we talk about an ionic bond, what we see is that we have a metal and a nonmetal. Remember, our metals are on the left side of the periodic table. So if I kind of sketch out a little rectangle here representing the periodic table, we're going to find our metals, okay, over in this region. And then we'll find our nonmetals kind of in this region. And we actually have kind of a sloping value where we convert from metal to nonmetal. So for an ionic compound, we have a metal and a nonmetal, and when we do that, we're going to actually have a transfer of electrons. So our ionic is metal plus nonmetal, and we're transferring electrons. When I look at a covalent compound, however, what I'm looking at is typically 2 nonmetals And what we see happening there is sharing of electrons. So the examples we looked at for forming those ions, the sodium became sodium plus 1, the chlorine becomes a minus 1. Sodium completely gives up that electron to chlorine. When I look at covalent molecules, what I see is that I have two nonmetals that are both sharing the electrons. The goal is still the same. The goal is still to get to that octet around the in the valence shell, the outermost shell. But what we have to worry about is making sure that the number of electrons is 8 for both atoms. Some of them will do that by transferring, as in ionic compounds. Some of them will do that by sharing, as in covalent compounds. As we go into more detail about these structures and about the types of compounds that form, you'll see more examples of these. I don't go into any examples really here. It's just looking at some of the general ideas before you watch those videos online. So what we also see to form ionic compounds are called polyatomic ions. Now we talked about ionic compounds being a metal and a nonmetal. And for the most part that is absolutely correct and that will happen, but we can also see polyatomic ions form. And so these are groups. So say we have this polyatomic ion or this polyatomic ion. Okay, these are all separate ions, and what it is that they behave as a group. So if you were in high school and that clique of girls that always went everywhere together and never did anything by themselves unless they were always with those same group of people, those were our polyatomic ions. They behave as a group, they act as a group. And so what we can see is that instead of having, say, an anion like chloride, we could instead have, say, thiocyanate, SCN minus. But what I see is that this SCN behaves as a group. We're not going to break it down. We'll see some more examples of these when we talk about nomenclature of ionic compounds and how we determine the formula, but just be aware that these are always acting as groups. Now, I can't just look at elements and say, well, of course that's a polyatomic ion with a -1 charge. We have to learn these. And so in your book, there is a list of polyatomic ions, and what we have is a list of these compounds or these ions, and these are something you just kind of have to memorize. Flashcards are great for this, whether it's a paper flashcard or an electronic version, but you do need to know this. You are responsible for knowing these polyatomic ions. The ones that are highlighted are just representing the ATE, and these are the most common ones we see, but we do see other versions. So we have nitrate, which is NO3 minus. Nitrite is NO2 minus. Notice that the ITE ending has one less oxygen than the ATE ending, and it has the same charge, and that pattern will continue. If I look at sulfite and sulfate and sulfite, sulfate has 4 oxygens and a 2- charge. Sulfite has 3 oxygens and a 2- charge. So one less oxygen, same charge. And that will be true for all of these oxyanions, so these polyatomic ions with oxygen in them. I see the same with phosphate and phosphite, carbonate, we don't have carbonite on there, chlorate and chlorite. So we see all of those happening, and we just need to memorize those. The best way to learn them is to practice them. If you practice your nomenclature a lot, it should make life much easier for learning the names, formulas, and charges on all of these polyatomic ions. So I think that gets us through the information you need before we do our groups this week in class. If you have questions, please feel free to ask them. There are some videos for ionic compounds already online. The covalent compound videos will be coming soon. And tomorrow in class, what we're in this week in groups, both tomorrow or Wednesday, we are going to be looking at the mole and how we use the mole in chemistry. What is a mole and what does it mean? As always, if you have questions, please let me know. Post them on Piazza, but get help and get those questions answered. Hope you've had a great day off and hope that you've gotten a little bit of chemistry done somewhere along the way. I will see you bright and early on Tuesday or Wednesday morning.